Okay, so today I'm going to be talking about a UNet convolutional network for biomedical image segmentation paper, and this was published back in 2015, and it should be really understood in that historical context. So let's start with introduction. Deep convolutional neural networks are the mainstay in visual recognition tasks. Okay, so that goes without saying. And For biomedical applications, object localizations are desirable, but in that domain, there's usually low amount of training data. So that's always an issue. So perhaps it's important for me to just give a quick review of the different kinds of computer vision tasks. So the different kinds would be image classification, when you just have an image and you're classifying it. We could have object localizations, whereby you have an image and you're localizing objects in that image. That would be an object localization task. But it could also be instant segmentation. So it could be a segmentation task, whereby you're really classifying things at the pixel level, which is what we're speaking to in this paper. So back to the point that usually you don't have the opportunity of millions of images in biomedical domain. So the network and the training strategy in this paper actually relied on a strong use of data augmentation to make sure that the available annotated samples are used effectively. So this paper is an improvement over the Reson et al. 2012 paper, which is just a sliding window setup to predict class label of each pixel. Okay. So setting these up, in fact, it should become obvious that this is going to be terribly slow. Imagine if you're just sliding the window and predicting class labels, okay? And also, there's also an obvious trade-off between localization accuracy and the use of context. Then what does that mean? When you have larger patches of images, then you will be required to do much more of max pooling. And this is a reference for a 2x2 max pooling operation, for example. But that reduces localization accuracy because you are using more max pooling operations, right? But then when you use small patches, then your network would not be able to see contexts that will be required for you to see to improve the localization accuracy. So that's the trade-off that's usually inherent with these sliding window method. So going forward with our introduction, but now talking about the solution, what they did in this paper was they built upon a more elegant architecture. So the so-called fully convolutional network. Fully convolutional network simply means there are no fully connected neural networks. They're not fully connected. And we'll get to see what that network is look like in a minute. So the modification that was of course made was to allow for fewer training samples and to allow for precise segmentation. So what's the basic idea behind this fully convolutional network introduced by Long et al. In 2014? It's just two main ideas. There's a usual contracting network by successive layers, whereby you can speak to, you can call that the contracting path, if you will, and then you also have this the other path whereby the pooling operators are replaced by hop sampling operators. Of course, then you have a kind of expansive path. So the downsampling part extract important features, while the hop sampling part give rise to outputs with a high resolution that allows for precise localization operations. Okay. So this is the UNet architecture. So the upsampling part does have, in fact, large number of feature channels. You can see the feature channels here: 512, 256, 256, 128, and so on. And this is in fact important so that the network will be able to propagate context information to higher resolution layers. And the consequences is this UNet architecture, right? This more or less symmetrical contracting path and expansive path giving rise to this U-shaped architecture. We're going to go into more details of what is really going on with this architecture in a minute. In the meantime, I should say that they use an overlap tie strategy. Again, they are not fully connected layers. They use valid padding, which simply means that there is no padding taking place. And to predict, so you can think of this image. So this is one of the figure in the paper which they are using to essentially illustrate the overlap tie strategy. So if you take this image, which is essentially what this is, um, and if you are classifying pixel in the middle, you can get context. But by the time you move to the border region of the image, then there's a missing context. So that missing context is extrapolated by mirroring of the input image. Okay, right there. So that's another strategy that was used in this paper. The other point to raise is that, of course, they have very little training data sets and they use excessive data augmentation by applying elastic deformations to available training images. And they also made some adaptations, and I will mention this once again when we start talking about the loss function. But the adaptation that they made was to somewhat the challenge of touching objects that are quite repeating quite a lot of biomedical image segmentation tags. But in essence, without going into more details here, the whole point is they introduced a weighted loss. They introduced they actually introduced the use of large weights for the separating background labels between touching cells in their weight loss, in their loss functions, such that the network can actually learn quite precisely, if it can, the background, so the not the backgrounds, the borders between these adjoining cells. Again, I'm going to speak to that once more when we start talking about the loss function. But again, so now let's go to the network architecture. The network architecture we know has a U-shaped architecture, as I have actually said. We have a contracting path, we have an expansive path. So we have a repeated application of two 3x3 convolutions. Again, it's unpadded. It's a valid convolution, and you can see that in the blue arrows. So it's a two 3x3 convolutions operation, and each of that is of course followed by ReLU. And then we have a 2x2 pooling operations with a stride of 2 for downsampling, and then you can see that in the red arrow. So 64 goes to 128, and 128 goes to 256. 256 go to 512. I'm talking about the number of channels here. So you can see that at each of these downsampling step, we have doubling of the number of feature channels. Okay. So now let's look at the expansive path. For the expansive path, every step actually consists of an upsampling of the feature map, which you can see in the green arrow. And this is a 2x2 convolution. You can call it a up convolution that halves the number of feature channels for each up convolution operation. So you can see from here 512, it becomes 256, 256 becomes 128, and so on and so forth. However, we also have the skip connections, right, that allows for the concatenations of the corresponding cropped feature map from the contracting path. So if you go back to the architecture, you can see that cropping going on, So this upsampling actually halves the number of feature channel, but then you have that cropping and you have 512 feature channels. And the reason for that is essentially, of course, it's because when that upsampling takes place, there's loss of border pixels in that convolution, and that cropping essentially is necessary due to that loss and to give more context in essence. So finally, you have a final layer, which is a 1x1 convolution that maps the 64 component feature vector to the desired number of classes. The number of classes is still, I believe in their case, the background and actually the cells in the image. In total, a network of 23 convolution layers was actually used. So let's again speak to the training. The optimization was a stochastic gradient descent implementation. And because they didn't use padded convolutions against valid padding, the output image is smaller than the input image by a constant border width. That should be said, and we've talked about that briefly. They also favor large input size over large batch size. So they reduce the batch size to 1, and because they are using one batch size, they're using a high momentum, such that a large number of previously seen training samples are required to update the current optimization step. Okay. What of their loss function? Okay, so what is their energy functions look like? So they computed it using a pixel-wise softmax. That's over the feature map, of course, the finer feature map. It's important to say, and that's combined with a cross entropy loss function. Right. So what? Let's start with a softmax per pixel. That's a pixel-wise softmax. So this expression essentially gives us the softmax per pixel. A subscript k of hex denotes the activation in the feature channel k at the pixel x, when here x is an element of the omega. K is the number of the classes, okay? And the p subscript k of hex is either approximately 0 or 1, 0 for all other case, 1 for k that acts the maximum, a subscript k of x, okay, the maximum activation. So then the cross entropy then now penalizes at each positions of the pixel, each pixel position, whereby we have the deviation of the softmax from 1. So you can see the entropy function essentially is you have the summation overall of the pixel positions. We have W of hex. We're going to speak to what hex is in a second. Then you have the log of this softmax per pixel that we are speaking to. So speaking to about the W, essentially this is a real number. I think it should be a real number. So let's go to, so in essence, you have this cross entropy, which is summing over all of these pixel positions and W of x with the log of the softmax, just like I've said. So what is this W of x? The W of x, without going into much details, is what I spoke to with regards enhancing border recognition. So this is an LSL that this is just a raw image. In B, you can see the overlay with the ground truth segmentation. In C, you can see the generated segmentation max. It has a white foreground, a black background. And in D, you can see the map with a pixel-wise loss weights, essentially that forces the network to learn the border pixel, and that's essentially what the W of X, okay, is doing in this cross entropy function. It forces the network to learn the border recognition, the border boundaries, if you will. So for the experiments that they did, I believe this is just a result from this ISPL cell tracking challenge back in 2015. In A, you can see part of an input image of these data sets. In B, you can see the segmentation results, which is a cyan max with a manual ground truth of the yellow boundary. In C, you can see the DICLR data sets and the segmentation the segmentation results in D. So the segmentation results are represented by high OU on the high SBI cell tracking challenge, and essentially, without going into much detail, compared to the state of the art then, UNet had a much superior, if you will, segmentation results of that's the high OU, and essentially just a a sort of, for folks who don't know what IOU is, essentially it's just the size of intersection. So you have the ground truth, you have the prediction, and the IOU gives us the size of intersection um, divided by the size of the unit. And of course, the closer to one that is, the much more predictive or accurate the segmentation is. So this is just something I drew up for some of the applications I believe I had in the lab. Um, so that will be the end of this talk, and thank you so much for listening.